Imagine you're at the station waiting for your train. Everything looks solid, reliable, right?
Hmm.
But have you ever stopped to think about what it really takes to keep a massive, complex machine like that train running smoothly day in and day out, not just for a few years, but for uh,
It's
decades?
a huge undertaking.
It really is. It's not just about building it perfectly. It's about strategically managing its entire operational life.
And that's exactly what we're diving into today. The crucial world of railway rolling stock, RAM management, and life cycle costs.
RAM management. Okay.
We're going to unpack what RAM stands for. That's reliability, availability, and maintainability, and how these three pillars are intimately connected to the total cost of owning and operating a train throughout its entire lifespan.
Right, the whole life cycle. So if you're someone who's curious about the unseen engineering marvels that ensure trains are, on time, safe, and surprisingly cost-effective, this deep dive is for you. We'll explore why this kind of management is absolutely critical, how it's actually done, and the fascinating challenges involved. Our mission today is to give you a shortcut to understanding this complex dance of engineering and economics that keeps our railways moving.
And the core insight here is that RAM parameters aren't just technical terms. They're the invisible blueprint determining whether a railway system can consistently deliver its promise of timely, safe service, all while staying on budget. It's really the long-term strategic cornerstone.
Okay, let's unpack this then. One of the most unique things about railway vehicles is their incredibly long lifespan. We're talking several decades, right? Maybe 30, 40, even up to 50 years with modernization and refit.
Exactly. That's a huge commitment.
It is.
And what's truly fascinating here, and perhaps a bit surprising, is how early those future costs are actually locked in.
How early?
Well, roughly 70 to 85% of a train's total lifecycle costs, or LCCs, are essentially fixed by the end of its design and development phase.
Wow, 70 to 85%.
Yeah, even though those costs won't actually be realized for years, sometimes decades later, during the train's day-to-day operation and maintenance.
That's incredible.
Think of it like this. The decisions you make when designing your house, how big it is, the materials, the heating system, largely predetermine your utility bills and maintenance expenses for the next 50 years, even before you spend a single night in it.
That's a great analogy. So the cost isn't just the sticker price, it's practically baked in before the train even hits the tracks, fixing costs decades in advance.
Yeah.
That's a huge deal. So what are railway operators doing about this? How do they protect themselves from those future costs?
So they're definitely building these RAM and LCC requirements directly into their contracts with manufacturers now.
Makes sense.
Absolutely.
Yeah.
They want to ensure that what they're buying today won't, bleed them dry in operations tomorrow. And there are often contractual penalties if these long-term targets aren't met.
Penalties, okay.
Yeah. And this prompts an important distinction. Operators usually focus on operational reliability, meaning does the train actually perform as expected in service?
Like, does it run on time? Does it break down?
Exactly. Things like avoiding immediate train stops, delays over a certain time, or disruptions to passenger comfort. Manufacturers, on the other hand, tend to focus more on inherent system reliability, which looks at the technical features of the components themselves.
Ah, so the bits and pieces.
Right. These are hierarchical, though. Operational impacts feed down to system and component level requirements. Maintainability is also key, and here's a critical insight. It's not just if a train breaks down, but how quickly you can get it back on track.
Right, the downtime.
Exactly. That's where maintainability comes in, measured by things like mean time to restore, or MTTR.
MTTR. Okay.
That's the average time it takes to diagnose, repair, and get a system back in service after a failure.
Mm.
A lower MTTR directly means less downtime and better availability. Simple as that.
That makes perfect sense. A train that's always in the shop isn't much use, no matter how rarely it breaks down initially. But how do you prove a train will meet these reliability targets over decades when you're just buying it? You can't just run it for 50 years in a test lab.
You certainly can't, no. The fulfillment of these requirements can only really be demonstrated during actual operation, usually over a defined, limited period.
So, real-world testing.
Real-world testing, but structured. This often involves statistical hypothesis tests, like sequential reliability tests, which are actually incredibly clever.
Sequential tests. How do they work?
Well, they allow manufacturers to determine if targets are met faster than traditional testing. Sometimes they can halt tests early once enough data is gathered to be statistically confident. It's a way to accelerate the proof without waiting, decades.
Clever. So, faster feedback.
Exactly. So when a rolling stock operator asks for bids, they either set firm RAM and LCC targets for the manufacturers, or they ask the manufacturer to propose their own. These committed values become a critical part of winning the contract. So manufacturers have to be incredibly competitive and savvy, carefully studying market needs, what their competitors are doing, and their own product experience.
That sounds like a complex balancing act right from the bidding stage.
Right.
And with all these sophisticated requirements, I can only imagine how challenging it must be to manage this across an entire train, especially since, like you said, it's rarely designed by just one team.
Oh, absolutely.
You have multiple divisions, external suppliers, each responsible for subsystems, individual components. So how do you take an overall reliability target for an entire train and break it down or apportion it to every single part?
That apportionment is absolutely vital.
I bet, for product development, for the supply chain.
It's a massive undertaking. This process involves both a top-down approach, breaking down the overall system requirements to individual components, and then also a bottom-up analysis.
Bottom up.
Yeah, where you estimate RAM and LCC values from individual parts and then build up to the system level. The ideal way to do this is through an iterative strategy.
Iterative, so back and forth.
Exactly. Continuously refining these estimates and designs in a back-and-forth process to meet the overall targets.
That sounds like a constant feedback loop. One of the big challenges I'd imagine is that environmental conditions, like extreme climate or very specific technical requirements, must have a huge impact on these RAM values.
Huge impact.
And they aren't always easily calculable. It's almost like trying to figure out how your car will run in 20 years based on its first few months. How do manufacturers even begin to bridge that data gap, especially getting accurate field data on how components truly perform in the real world beyond the warranty period?
Yeah, that is incredibly difficult. Getting that real-world data, especially long-term, is tough. Manufacturers often rely on specialized maintenance contracts or partnerships with the operators.
So they need that close relationship.
They do. To get that valuable real-world feedback and close that data gap, it's a critical part of continuous improvement.
Okay, so once a train is built and running, keeping it in top shape isn't just about fixing things when they break. Maintenance engineering itself sounds like a whole discipline.
It absolutely is.
Yeah.
It's focused on applying engineering concepts to ensure ongoing availability, reliability, safety, and, of course, cost-effectiveness.
Right.
It's deeply intertwined with RAM.
Right.
Traditionally, maintenance might have been scheduled simply by mileage or calendar time. Change the oil every 5,000 miles, whether it needs it or not.
Which often led to excessive downtime and costs, I imagine.
Exactly. You change something just because the calendar said so, even if it still had plenty of life left. But with today's complex mechatronic systems, these combinations of mechanical, electronic, and information technology, that's just no longer enough.
So what's the alternative?
We've moved firmly towards condition-based maintenance.
Condition-based, meaning?
Meaning, tasks are scheduled based on actual monitoring and inspections of the system's current state. What condition is it actually in?
Oh, okay, that makes more sense.
And we've advanced even further to predictive maintenance.
Predicting failures.
Essentially, yes. It aims to predict the remaining useful life of a component, anticipate failures before they happen, and determine the optimal time for intervention. Not too early, not too late.
Optimal. Right, and I think I read something about going even further than just predicting.
You're probably thinking of prescriptive maintenance.
Prescriptive, yes. What's that?
So that's not just predicting a fault, but proactively controlling operating parameters, maybe slowing something down slightly, or suggesting specific actions to prolong a system's life. And it does this based on things like cost structures, schedules, user priorities.
Wow, actively managing the system's operation based on predicted health.
Precisely. And then we have the umbrella term, Prognostics and Health Management, or PHM. This gives an integrated view of a system's health. PHM encompasses fault detection, diagnostics, prognostics, that's the prediction part we talked about, and then crucially the health management piece, to take optimal actions based on all that information. It ties it all together.
That's quite a progression from just fixing things when they break. So how do engineers decide on these advanced maintenance plans? What methodologies do they use?
Well, to determine these plans, two common, really powerful approaches are often used. Reliability-centered maintenance, RCM, and risk-based maintenance,
RCM and RBM.
RCM focuses on maintaining the function of a system, not just a specific component failing.
The function, like braking, not just brake pads.
Exactly. It's a structured process that asks 7 core questions. What is this system supposed to do? How could it fail to do that? What causes that failure? What are the consequences if it fails, and why does that matter to our operation?
Right.
And then crucially, how can we prevent that failure? Or what's the plan if prevention isn't feasible? RCM integrates really well with powerful tools like failure mode, effects, and criticality analysis, or FMECA.
FMECA, I've heard of that.
Right. It's essentially a systematic process to identify how a system can fail, what the effects of that failure would be, and how critical those failures are. RBM, on the other hand.
Risk-based maintenance.
Yes, that specifically focuses on reducing risks, and not just safety risks, but economic and operational ones too. Where is the biggest risk exposure, and how do we mitigate that through maintenance?
Interesting. So RCM focuses on function, RBM focuses on risk. Do they use one or the other, or?
Actually, interestingly, in practice, engineers often combine the most effective elements of both RCM and RBM to create truly optimized maintenance programs.
Ah, so they blend them. Why blend them? Why isn't one sufficient?
That's a great question. Well, RCM is excellent at ensuring functional integrity and identifying tasks for specific failure modes, but it might not always fully prioritize risks beyond the immediate operational impact. Okay.
RBM, conversely, excels at risk reduction and economic optimization, but might not always delve as deeply into all the functional failures across the whole system.
I see.
So by combining them, engineers get a more holistic view. They ensure critical functions are maintained, that's the RCM part, while also proactively mitigating the most impactful risks. Financially or operationally, that's the RBM part. It leads to programs that really balance safety, performance, and cost.
A pragmatic approach.
Yeah.
Taking the best of both.
Exactly. But this intricate balancing act leads us straight into the inherent conflicts in RAM and LCC management.
The conflicts.
Yeah, think about it. Different countries, different customers, they all have unique operational environments and requirements. So no two train offers are ever truly identical.
Right. Customization is key.
Which creates higher commercial risk for manufacturers, especially with newly developed systems where the uncertainty is naturally greater. I can definitely see that. And it must be incredibly complex for everyone down the supply chain, too. Passing on those really precise RAM and LCC requirements isn't always straightforward, is it?
Not at all.
Yeah.
For instance, expecting a component supplier to know the precise exchange time for their part when they don't design the entire train's accessibility.
How easy it is to get to the part, yeah.
Exactly.
Yeah.
Or asking them to reclassify failure rates for every single project's specific unique categories. It just increases overall project costs and, frankly, coordination headaches.
Yeah, that sounds like a nightmare.
So this raises that important question again. How do you balance these sometimes contradictory goals and capabilities across such a complex system?
It sounds like the key is realistic apportionment.
That's a huge part of it. A balanced apportionment of RAM LCC requirements that truly considers the real capabilities and limitations of subsystems helps reduce project costs and the risk of needing expensive redesigns later.
Makes sense.
But sometimes a change you make to improve RAM might conflict with other design properties.
Like a trade-off.
Precisely. For example, maybe you enlarge a wheel diameter to reduce how often you need to exchange it that would improve availability and lower LCC.
Good.
But that larger wheel might conflict with the available installation space within the train bogie, or it might exceed limits on unsprung masses, which affects ride comfort and track wear.
Ah, so fixing one thing potentially creates another problem.
It's always a trade-off. And perhaps the biggest paradox in all of this.
Go on.
Meeting high operational reliability targets often involves adding a lot of redundancies to a system architecture, backup systems,
Right, makes the overall train less likely to stop.
Exactly. It increases the product's operational reliability, but simultaneously increases the product's purchase price and its maintenance costs.
Because there are more parts to maintain and potentially fail.
Precisely. You're building in more components that need checking, servicing, and might eventually break, even if the system as a whole is much less likely to suffer a complete failure. It's this constant, nuanced balancing act between competing objectives.
Wow. So as you can see, managing reliability, availability, maintainability, and lifecycle costs for railway rolling stock is, well, it's a sophisticated, multifaceted process that spans decades.
It really is.
It's about designing for longevity, predicting potential issues, optimizing maintenance, and constantly iterating based on real-world performance, all while juggling complex contracts and these conflicting goals we just discussed.
And it's truly a testament to the ingenuity of railway engineering teams. They have to constantly synthesize vast amounts of information and feedback to keep these massive, complex systems operating efficiently and safely.
Every single decision made early in the design phase just ripples through the entire operational life of the train, doesn't it?
Absolutely. Impacting everything from punctuality, safety, passenger comfort, right down to the operator's profit margins.
So here's a final thought for you to mull over as we wrap up. As railway systems become even more interconnected, equipped with ever more advanced sensors, AI, what will be the ultimate impact on RAM and LCC management?
That's the big question for the future.
Will we reach a point where trains can truly self-diagnose, self-optimize, maybe even prescribe their own maintenance, pushing the boundaries of what's possible in terms of uptime and efficiency?
It certainly seems like the direction things are heading.
And what implications might that have for the engineers and operators of the future? Something to think about.